Hi everybody, welcome back to the Feynman technique. Today we'll be taking a look at these two integrals and we will be using the same process to solve them that I've been using in the last four videos in this series. So go ahead and check those out if you want to see some other integrals solved with this same exact technique. I'm going to be moving a little bit faster through this one since the technique should already be somewhat familiar to you at this point. So, as in the previous videos, we are going to be starting with a known value. In this case, it will be a known value that I derived in the previous video. That is that the integral from 0 to infinity of natural log x over x to the fourth plus 1 integrated with respect to x is equal to negative square root of 2 times pi squared over 16. Go ahead and watch my previous video to see how I derived that. Okay, next, what we're going to do is consider this integral, which is just this integral, except with an a to the fourth replacing that 1. And that's no coincidence. If you've watched my previous videos, you probably know exactly why I did that. Okay, and then from here, we factor out a 1 over a to the fourth. Then we make the substitution, u is equal to x over a, implying x is equal to au and dx is equal to a du. And next, we plug in that substitution right here. You'll see we'll get a 1 over a cubed due to the fact that our dx is a du, canceling one of these a's here. Our bounds of integration are not going to change. We will get not natural log x, but natural log au. And then it will be not over x to the fourth over a to the fourth. That is simply u to the fourth. 1 does not change. Dx again becomes an a du. And then we use the properties of logarithms to split this integral. Notice that natural log au is just natural log a plus natural log u. And you can see we have our natural log a plus natural log u. So we just split that integral using the properties of logarithms. All right, now applying our known value to this integral right here and the well-known value of this integral, which is pi square root of 2 over 4. Evaluating this integral, we get pi square root of 2 over 4. And this one is the known value that we started with. Subbing those in and simplifying, and we get this. So we have that this integral right here is equal to this. All right. Next, we're going to sub the value a is equal to I to the 1/4. I to the 1/4, its principal value is e to the I pi over 8. Okay, and the reason I did that was because if you raise I to the 1/4 to the fourth power, you just get the imaginary unit, and that's the whole point. We want the imaginary unit to appear here. Again, watch my previous videos and you'll understand why I want to do that. All right, and then of course we have to substitute I to the 1/4 or e to the I pi over 8 in for all our a values here. All right, performing that substitution or plugging in that value for a, and we get this. I literally just plugged in e to the I pi over 8 over here and I to the 1/4 right here, giving us the integral from 0 to infinity of natural log x over x to the fourth plus I dx equaling this. All right. And next, I just want to just kind of rewrite this. Basically, all I did was I used Euler's formula on e to the negative 3I pi over 8. And that's right here. That part is right here. Of course, we have our pi square root of 2 over 4 right here. And then you'll notice natural log and e cancel each other out, leaving us just this. So now we have this. Don't forget, this part right here is actually this. We'll be using that later. But for now, this is equal to this. And then we need to kind of state the values of cosine and sine of 3 pi over 8. Those are not well-known trig values, but they're easily derived using the half-angle identities for sine and cosine at pi over 4. Or I should say at 3 pi over 4. Okay, so plugging those values in and doing a lot of doing some algebra, distribution, blah, 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 separating the real and imaginary parts, and we arrive at this. I'm not going to show that step by step. You can do that yourself. Just plug in these values appropriately, FOIL this part out, distribute that, and then separate it into its real and imaginary parts right here. Okay. But don't forget, this part right here was this integral. So, and by the way, this integral is also equivalent to this simply by multiplying the top and the bottom of this integrand right here by x to the 4th minus I. Of course, x to the 4th minus I times x to the 4th plus I gives you x to the 8th plus 1. All right, so this is equivalent to this, which in turn is equivalent to this. So we are almost done. So just restating what I just said, this integral right here is equal to this quantity. So now all we have to do is match up the real and imaginary parts, which is very easy. This easily splits into a real integral minus an imaginary integral, or I should say a real integral multiplied by the imaginary unit. So we have this is equal to this, matching up the real and imaginary parts, and we arrive at the solution to our original integrals up there. Pretty messy, but you know, that's the answer. Those are the answers to those integrals right there, and those integrals would be extremely daunting without using this technique that I just showed you right here. I'm a big fan of complex numbers, not a big fan of contour integration, just because that requires you to know a lot of theorems and rules that are difficult to prove. Whenever I solve integrals on my channel, I like to be able to prove why every step I do is true, or at least to know it. I like to know why every step of the process is true. Now I can do contour integration, but some of the reasons why it works are still a little bit foggy to me. I'm still learning a lot because I do not have a formal education in mathematics. Everything I know about math, I've learned off of basically other YouTube channels. So anyway, that's the answer to those integrals. I hope you enjoyed that, and we will see you next time.